In this question, we're going to look at how to delete a node in a binary search tree. Okay, so let's give you an example to start with, and then I'll explain the strategy which I'll follow to solve this question. So here's a tree. I'm referring my copy for this. I made a sample tree for you. The example needs to be complex enough so that I can cover all the basic conditions which occurs in these kinds of questions. Okay, that is why. So yeah, this looks complex enough to me. Okay, let's assume we want to will be provided with a key, and that key is the value of the node that we want to delete. Okay, in our case, let's assume it to be 10. So 10 is our root node. Okay, let's assume we want to delete this particular node. To start with, I'll tell you what our final result will be. Our final result would be 9, 7, 8, 5. Make sense? It won't make sense, but this is our final result. In this case, we have removed a value 10 and we have arranged the tree in such a way that it is a valid binary search tree now also. We're not just blindly removing a node, we are finding its replacement. In this case, it's 9. I'll tell you how 9 has come, okay? But this is what our final result will be. Now, let's see how to solve this question, okay? So, we know that in a binary search tree, a value to the left is always smaller value and a value to the right is always a greater value. Fine. So let's assume if key is lesser than root.val, then we need to jump left. Okay. Else if key is greater than root.val, then we need to jump right. Okay, right now all I want to do is find that particular node which needs to be deleted. In our case, I've given it as 10 just because the complex conditions can be covered now. I could have given an easier node 8 and I could have just, that result would be very easy, but I've chosen a complex enough example. Okay, so now comes the main condition, which is else, where we have finally found the node which needs to be deleted. Okay, now how do I delete a node? You can think of several practices. I'll explain my particular strategy. Okay, so we have two ways to do this. Number one, there are two approaches. Okay, we can use in order predecessor or use in order successor. Okay, these are two approaches I'm aware of. I'll go with this one. Okay, in order predecessor. What do I mean? First of all, what is an in order traversal? I'll show you what an in order traversal of the tree I showed you above would be. In order would be, it would be 5. I'm referring my copy because there the tree is still made. Okay, 5, 7, 8, 9, 10, 11, 12, 14. Okay, yeah, this is what it is. This is a root node and this particular thing is a successor, is a predecessor. Okay, so what do we do with this predecessor? I'll explain you. So these are the steps to solve the problem now. Okay, number one, find predecessor. Just in case you don't know what in order is, so for binary search tree it's very easy. It's just a sorted list of node values. Okay, in binary search tree, whenever you find an in order, it's always a sorted this can be anything. It can be a vector or anything, but it will always be sorted. Okay. Find predecessor, replace it with root, and the third step would be remove that predecessor. Okay, I'll show you how to do things. Okay, I'll draw back the tree which we have. 7, 5, 8, 9, 12, 11, 14. Step number 1 would be finding a predecessor, which is 9 in our case. Okay. Step number 2 is replacing the value of root, this is our root, with the value of predecessor. Let's replace it. 9, 7, 5, 8. Okay. The last step would be removing this particular predecessor. So let's remove it. So our final result would be and by the way, this removing a predecessor is just a recursive step. So our key was earlier 10, now our key to be deleted would be 9, and instead of root we'll pass root.left, that in this particular left tree we have to delete a node with a value 9. Okay, it's just going to be a recursive step. It will be very easy, but here we go. Our problem consists of 3 steps: finding a predecessor, replacing its value with a root node, and then just deleting that predecessor. And here we have it. I'll go to LeetCode, I'll code out the solution for you, and in case I've missed some crucial explanation, I'll explain it there only. Thank you. Okay, turns out I did miss something, which is how do we find predecessor? Okay, how do I? So they are just 2 simple steps. These are very common sense based steps, but I'll write it down for you. Okay, start left once, go as right as possible. Okay, these are the 2 steps. I'll draw the tree again for you and we'll find our predecessor together. Okay, what is the step? Start left. Okay, so this is how we start left. Okay, what are we left with now? 7, 5, 8, 9. Next step is go as right as possible. Okay, let's go as right as possible. Here we are. This is our ending point. So our predecessor is 9. Okay, it's a very simple while loop. It's nothing. It's just how we find predecessor. Okay, see you at LeetCode. Bye bye. Everyone, welcome back. And first of all, in the previous explanation video, I told you how to find a predecessor. Now why are we going just to the left side? Just because a predecessor is a value just smaller than a root node, and that will be found only in the left side of the tree. That is why we started left and then we went right, because now we want to find the largest value which is smaller than the root node. Okay, just think about it and you'll get it why I am choosing that particular way of finding a predecessor. Okay, right now let's just go to the question. First of all, we'll have to make sure that the root is not null. Okay, if the root is null, just return a null pointer. Okay, we won't even handle that. We'll just start with if the root is not null. Now first of all, I told you a condition that first of all we need to find the node to be deleted. Okay, so if the key is lesser than root.val, then dot left is equals to delete node dot left key. Okay, else if key is greater than root dot val, we do root dot right, delete node root dot right key. Now what am I doing here? I'm just saying that if the value of key is lesser than root dot left, then the root dot left will get updated. How will it get updated? Recursively. This is how root dot right will also get updated. If we have this example 1 and we want to delete a node number 6 or maybe a node number 7, then entire things will change. That is why I've done root dot left is equals to whatever our recursive function will return us. Don't worry about it. Now comes to our main step, okay, where the value of the root node is equal to the key. Okay, now we have to check a few basic things. First of all, if the root node which we are at doesn't have any siblings, doesn't have a left or a right child, then we have to return, let's assume it's the only node in the tree. I showed you an example right in the explanation video. Then just assume there is a single node and that single node has a value equal to the key. What we'll do, we'll just return null because it doesn't have a left or right, so we cannot find a predecessor or successor or anything. We'll just return null. Okay, so let's just handle this step. Null pointer. I'll write down the comments. No children. Okay, in case of no children, we'll do this. What if it has just one children? What if we want to delete a node 5? Okay, this example 1, I'm talking about example 1. We have to delete the very root node, but assume this 5 doesn't have a right tree. Those nodes 6 and 7 doesn't exist. Then what will it do? We'll just return the left value, right? Our result would be 3, 2 and 4 in that case if it doesn't have a right tree. And same is the case for vice versa. So either children not present, then what will do? Else if, we'll write an else if not root dot left or not root dot right. Okay, if one of them are not present, return root dot left. What am I doing here? This is just a ternary operator. What it is doing is, it is checking if root dot left is not null, then return that, otherwise return root dot right. Okay, that's it. Now we are at the main condition where the value of the root node is equal to the key and it has both children. This is where we want to find, we need to find our n order predecessor. Okay, we'll do that. Tree node temp. What did I say? Start with the left node, right? We'll do that. And this is step number 1. Okay, step number 1 is start left. Okay, step number 2 is go as right as possible. Okay, we are finding a predecessor now, right now. Okay, this in our overall logic, this was step number 1. These 2 steps are for finding a predecessor, but in our overall logic, our step was to find an unordered predecessor. So this is what we are doing. So how will I'll just do temp. Okay, we are going as right as possible. We have finally found our predecessor. What will it do now? Replace it with root node. Its value with root node. There's a difference in both of these. So root.val is now temp.val. Okay. We have replaced the value. Now we want to delete the predecessor. This also I've told. How will you do that? Our root.left will get updated. Okay. Delete node. What did I tell you in the explanation video? We'll go to the left tree now, and I told you that last step is a recursive step. We'll go to the left tree and we'll delete the value of predecessor now. Okay, our value of key is changed now. Our new key is the value of that predecessor. We want to delete that thing. Okay, just refer to my explanation video and everything will be clear. Just return root now. Let's see if it works. Where did I go wrong? Okay, I'm sorry. Let's see. This should work. Okay, I think it's working. Let's try submitting it. Done. It's working. I hope you got it. If you have any queries, just feel free to write it down in the comment section and I'll be there. Thank you.